Hello, everyone, and welcome. My name is Enrico Cray. I am the chair of the Debug Working Group and moderator for this session. I would like to introduce Thomas Presser from Asemic Technologies. Thomas leads the research team at Asemic in Dresden, Germany, and his research interests include massive parallel computing acceleration and data processing in heterogeneous FPGA-based systems. Thomas will start off the session with the presentation, and then we'll conclude with a live Q&A session. Questions can be submitted in the chat area. And I'd like to remind everyone that the presentation can be downloaded from MIPI.org and refer to the link in the pre-populated chat area. Thank you, and we'll get started.
Hello, everyone. This is Thomas of Asemic Technologies. I welcome you to our presentation demonstrating MIPI protocols as the foundation of next-generation analysis of multicore processors. Let's have a look at why we're doing what. It's been shown over and over that non-trivial software is prone to errors. Ever pushing the complexity of software systems not only increases the defect potential, also the efficiency of the detection and removal of these defects is crippled. This is why the capabilities of tools and processes must advance in order to obtain manageable solutions. A key capability for this process of system validation and debugging is the observation of the system. Embedded applications regularly pose particular observation challenges. You may have real-time controls that simply cannot tolerate any logging delays or even breakpoints. But oftentimes, already the convoluted interaction of multiple concurrent actors creates systematic hardships. For example, complex Mandel bugs often become hard to reproduce and hence to observe when they depend on unknown required site conditions. This greatly impedes the ability to gain insight and understanding about the underlying issue. A desperate choice of intrusive probing may then even produce Heisenbugs that are masked away by the very means introduced to find them. In consequence, plain printf debugging or even well-automated software instrumentation are regularly more harm than useful. All in all, there are two desirable system observation properties. First, non-intrusiveness, so as to obtain a faithful picture of the system operation. And second, continuity, so as to catch anomalies that occur infrequently. These properties are also key for innovative observation use cases on the system level that go beyond debugging. For example, system health monitoring and continuous runtime verification. These applications are particularly interesting in fully integrated field deployments. Let's have a look at the state of affairs. A long time ago, a simple logic analyzer on the system bus would essentially reveal all detail of a system's operation, the instructions executed, and the data processed. Both are observed on a clean timeline. Advancing system integration and speed are not only inflating the volume of execution data, they're even hiding it inside on-chip subsystems like memory hierarchies with caches. The concurrent and increasingly truly parallel execution of tasks within a single system severely complicates the effect attribution for an observer who is confined to the outside. It takes a designated embedded trace infrastructure facilitated by on-chip probes to recover carefully chosen observability. Trace filters and high-speed interfaces are the means to cope with the immense produced data volume. Three alternative trace analysis options are used in practice. The first and cheapest option uses regular system memory for buffering short trace snippets for the later offline analysis. This approach is clearly intrusive and non-continuous. Non-intrusiveness is achieved by the second option. It uses a designated external trace interface to connect an external trace logger. However, its trace buffer size sets a hard limit to the observable time interval, which thus still defeats continuity. It's the online processing of the third option, which finally achieves both non-intrusiveness and continuity. Its implementation, however, is hard, as the trace processing speed must match the trace generation. Several MIPI protocols define solutions for the efficient transmission of trace data. The link layer technologies, HTI and PTI, facilitate the off-chip transmission. The transport layer protocols, STP and TWP, allow to designate and share the available trace bandwidth between multiple trace sources that represent various trace aspects. The parallel trace interface, PTI, features a parallel data bus of up to 32 bits. They are transmitted synchronously to a single common clock. PTI allows bus slicing and data striping to accommodate multiple streams and differing word widths. Its protocol part also defines the signal calibration procedure to adjust for potential delay skew across the parallel data lines. The high-speed trace interface, HTI, exploits the power of serial transceivers. It boosts the achievable interface performance by more than an order of magnitude to tens of gigabits per second. A session management protocol ensures the coherent transmission and reassembly of trace data across all the lanes used. A selection of user flow control messages is available to convey sideband information such as triggers and overflow conditions. On the transport level, MIPI also offers two alternative protocol options. The system trace protocol is the Swiss Army knife. With vast multiplexing capabilities, standalone timestamping, user sideband channels, and integrated data integrity protection. STP is able to funnel and manage more than 65,000 concurrent trace sources. It is thus well capable of handling even vigorously integrated systems. The somewhat older trace wrapper protocol can still distinguish 111 multiplex trace streams and convinces with an extremely low protocol overhead. Many modern ARM processor systems with core-side support embody a stack of MIPI protocols. A typical protocol stack implemented by more recent architectures combines the trace wrapper protocol with an underlying high-speed serial transmission. On top of the transport layer, various trace sources may be implemented and combined. A plain program flow trace, a more versatile embedded trace macro cell, instrumentation, or system trace. For a quick recap of our key embedded trace properties, note that the MIPI protocol family establishes the base for a non-intrusive continuous trace transmission. Lately, some system vendors started to adopt other standard interfaces, such as USB, PCI Express, and Ethernet, to offer competitive alternatives on the link layer. On the transport layer, STP is currently just unfolding its momentum for dominating implementations. On the higher protocol levels, vendor-specific proprietary protocols beyond the scope of MIPI are the norm. They all still feature an enormous amount of commonalities, that can be attributed to their shared purpose of efficient trace bandwidth utilization. It is the sophisticated data reduction and compression techniques used here that create particular challenges for the continuous online processing of execution trace at line rate. First, let's review the benefits and application use cases of such an online processing. Most importantly, the continuous online trace processing eliminates any systematic observation time limits. Additionally, the processing pipeline drastically shrinks the analysis latency down to a few milliseconds. This enables essentially instantaneous reactions, unfolding a completely new host of application domains, for instance, in security. If based on a designated external trace tool, this approach is also completely non-intrusive. Without an observation time limit, the online analysis conquers new magnitudes of scale. For example, structural coverage measurements scale beyond elementary unit tests and can be performed on high-level integration and even system tests. Continuous runtime verification and WCET measurements can be extended to the production application deployed in the field. To appreciate the processing challenge, consider this representative short example of an Intel PT processing trace. Only occasionally a complete absolute synchronization point and decoding context is established by the trace protocol. Here, this is the PSB packet, which can be identified even within an unsynchronized trace stream. All packets other than the PSB are encoded in a variable length prefix code that depends on a proper synchronization on packet boundaries. The actual context information is contained within a block following the PSB. Assume our example to start at the program address 400-220. From there, only so much information is communicated to enable an observer to reconstruct the taken control flow under the condition that it also knows the executed object code. In particular, sequential, and in this case unconditional control flow is silently implied. Thus, the subsequently communicated not taken indicator refers to the next encountered conditional branch, which here is only encountered beyond the unconditional and hence silently executed function call. Further addresses, as for indirect branch targets, are only communicated as compressed patches against the last known value. This encoding is exemplified for the return address in the sample trace on the left. As shown on the right, return addresses are often further reduced to a single bit taken indicator, as long as an observer can be expected to infer this address by maintaining its own shadow call stack. As illustrated in this example, this encoding regularly entails other benefits, such as the aggregation with other surrounding execution indicators into a single byte TNT packet. In summary, the reconstruction of the control flow requires both a trace data decompression and its interpretation against the static control flow graph of the executed application. Any non-trivial application will require this control flow graph to be stored on sizable external memory. The access latency of this memory must be mitigated in order to ensure a processing pace at line rate. This typically requires a concurrent and interleaved processing of the trace data. This picture shows our physical setup that enables an online coverage measurement, even on the system level. The trace target exposes a trace interface, that feeds an intelligent trace tool. The trace tool, on the right, features an FPGA-accelerated trace decompression and interpretation, which is backed by a refined representation of the control flow graph of the executing application. On this basis, the relevant execution statistics are collected. After readout, the execution statistics can be annotated back to the object code, as shown on the left. Individual execution counts are identified for each instruction. In the case of branch instructions, the observed sequential continuations and branch outs are reported separately. With debug information at hand, also a visualization in the domain of the original source code is possible. This is shown on the right. This way, a test engineer can identify and handle test coverage deficiencies intuitively. The certification of safety-critical systems regularly asks for some higher-level coverage metrics, such as MCDC. This metric requires to keep additional statistics beyond tracking elementary branch edges. Here, the concrete path for deciding a multi-condition decision must be uniquely identified. In the shown minimal example, a valid complete test must demonstrate to execute the final negative decision outcome after evaluating condition C, both after taking the shortcut upon A being true and after taking the alternative longer evaluation path upon A being false. By extracting such path statistics from the trace of a monitored test run, the online trace analysis conquers a tremendous field of applications. It scales all the way to in-field production systems and into the safety-critical domain. For a brief summary of the utility of MIPI, we want to emphasize that our work greatly benefits from architecture-independent MIPI protocol layers. They enable efficient reuse and allow us to focus quickly on adding value on higher functional levels. However, we have also encountered challenges that might be overcome by a more thorough standardization of new developments. First, the use of alternative standard interfaces, such as PCI Express, sometimes also entails the use of non-standard transport mechanisms. This impacts reuse benefits. Standardization efforts, acknowledging the existence of alternative physical implementations, should demand to stabilize adjacent protocol layers. Second, the supported trace interface bandwidth does often not scale at the same pace as the overall system integration. This is risking the creation of physical bottlenecks. Standardized trace capability ratings could help to classify trace-enabled systems transparently and reliably. Last, but certainly not least, the timing slack between the trace streams multiplexed over TWP or STP may become arbitrarily large. In implementation, serving a low bandwidth trace source through an input buffer may result in unbounded delays of data in this buffer with respect to other streams. This creates enormous issues for the online reconstruction of a consistent timeline across different trace sources. Guaranteed time limits on data buffering would definitely be helpful. For further information on software engineering practices and economics, in particular test and debug, as well as on our work and solutions, you're kindly invited to consult these references. Please reach out to us for questions and ideas. We greatly appreciate your kind feedback. Thank you very much. We're looking forward to your feedback and your questions.
Thank you, Thomas. now we're going to move into our live Q&A session. For this session, I'd also like to introduce Alexander Weiss, who is co-author on this and a colleague of Thomas. As a reminder, for the Q&A, please submit your questions through the chat. Okay. All right, so let's get started. So the first question to get us going here is what design choices in the MIPI protocols have produced avoidable challenges for the online analysis?
Thanks for the question. A particularly interesting protocol is STP, so the upcoming Swiss Army knife for the transport layer. And if you look at all the functionality, what you will see is that it's really comprehensive, and some of the parts are really questionable if they need to go into the transport layer, and if they are not already covering functionality that would be above. And in the end, you have something that might overlap with other functionality in the protocols that are actually transported and duplicated. For example, timing information, there's extra sideband channels. And if you have an overlap of functionality, you're always running into the problem of potential inconsistencies. And that could be or should be cleared up and kind of kept on the table when you're designing solutions for these protocols.
All right, great. Let's see. What parts of the online trace processing pipeline can be expected to define bottlenecks in current or even future system implementations?
For the online trace processing, there's actually several bottlenecks because it is challenging in every single part. So there's some things that cannot be dealt with by MIPI protocols because they're out of scope. The high-level trace interpretation, for example, which, as you have seen, depends on a representation of or knowledge of the application that is executed, requires huge data structures in the background that facilitate fast lookup operations so that you can keep up with the pace of the trace that is coming in. But these things, these challenges are completely outside of what MIPI can deliver. The major bottleneck MIPI has to deal with is bandwidth, plain bandwidth, to make sure that the vendors that produce chips and kind of design the interfaces that are available are kind of at least motivated or even made to make sure that the bandwidth they provide scales with the functionality that they put onto the chip. So if you kind of scale up with additional cores, additional functional units, you add trace sources, that there's always a sensible notion to be able to trace what's on there and not just have some kind of trace interface, but which is always kind of too weak for every sensible solution to produce any informative output.
Okay. Other questions? Please, again, as a reminder, please put your questions into the chat window for Thomas.
Maybe a comment from my side to the last question. I think it's also important to design the chips without any influence from outputting the trace data to the other structures of the system, because it's quite important, to have no interferences there. Yeah, and this is also getting more and more important if they are used as standard interfaces like PCI Express and so on, because if you want to do some real-time measurement, then it's not a good idea to disturb your bot system by huge trace messages and so on.
Other questions? Everyone's kind of quiet today. Let's see. Alexander, is there anything else that you wanted to add? I know Thomas presented. Was there anything else you wanted to highlight?
Yes, in this presentation, Thomas told mostly about understanding what's happened inside the processor, but the same effort we spent for a high-level computation of the results of the control flow reconstruction. This is first, it's measuring control flow coverage. And second, I think that's much more important. This is the ability to do some event stream analysis, and therefore we have developed a high-speed, let's say 100, 150 megas events per second, a high-level language programmable event stream processor. And it's not enough to reconstruct the control flow. You also need the other components which helps you to place the right questions to the system and getting the answers in real time with low latency. Okay.
Great. Thank you. Again, any other questions? Double checking here.
Maybe a question from our side to you, Enrico. Are there any activities planned to further development of the trace-related MIPI standards?
So there are discussions inside the working group on some of the specifications that you've been talking about, and looking at bandwidth as one of the things, as you mentioned in your presentation. So these are ongoing discussions, and we are looking at those things. So
Okay.
And I encourage people to participate. If you are a contributing member, and come and join us for those discussions and give us some ideas and things like that.
Yeah.
So, yep. So we're getting close to the end here. Thanks again. Thank you, Thomas. Thank you, Alexander, for presenting today.